Coś tam chce daleko. Yeah.
Just looking into which, I'm just looking into which exact presentation, lecture to give you. Let's say, we can do with that one. Okay. Okay, so should we still wait for a couple of students, or can I start? Up to you.
You can start. I think most of them are already here, so you can start.
Okay. Then in that case, let me share the screen properly. I think, let's see this one.
Yeah, we see the screen.
Yeah, but then we need to, yeah, if I start the presentation now, what is that? Doesn't matter. Okay, yeah, I knew that. Yeah, I need to switch the screen layout. Just a second. How do I do that? Slideshow.
Yeah, the first one from the beginning.
Yeah, but then it's, yeah, this one. Yeah, now it's on the screen.
Yes, cool.
And you see it, right?
Yeah.
Okay, so maybe I can just briefly introduce myself. Yeah, this will give you a bit of a context to this lecture. So currently I'm a PhD in BTU Cottbus in Germany. I live in Poland, but I travel there every now and then. I actually teach students there weekly, so we have classes. But in the meantime, I have to write my PhD, and it's a very slow process. So my PhD, maybe let's start with the title of my PhD thesis, which is the current title. It might change, but it is representation methods for architectural, for AI in architectural design. So what it means is that I would like to focus on AI in design, but from a standpoint where we assume that we are just not able yet to give the AI the right information from architecture, right? So this is why we worry about the representation method. Representation is basically how we represent or how we write down what we can see in the observations, right? So in architecture, yeah, that's a good question. What are observations in architecture, right? Because if you apply the same logic to any other discipline, like, you know, writing down observations in biology, right? You have a very clear way of writing down the right information to give you some I mean, writing down the right data to give you some information, right? You know, there is this ladder of raw data, information, and knowledge, right? And this is where you get later on some wisdom. That's the basically the knowledge ladder. So in biology, for instance, when you want to get some information or actually some knowledge about the environment, you start with raw data. So your representation in biology, for instance, may be a model of, I don't know, a frog, let's say, right? So you will write down, how long is the frog, how green it is, what are the eyes like, or, you have very concrete information, very easy to evaluate, right? So you can just measure stuff and compare it, and that's how you get the data, right? In architecture, we have, I think, in my honest opinion, in architecture we have a problem with defining the scope of data which you would like to get, right? So I think that the problem is we don't even know what to measure. Okay, so why is that? It's very easy to measure square meters, right, and volume of a building. It's easy to measure the color of the building, but any architect will tell you that that doesn't really matter. In the end, what matters is a subjective experience, right? So you may know that in architecture, like in classical architecture, they made all kinds of different optical illusions, basically, to uh, appear, I don't know, bigger, longer, deeper. Yeah, but it was all tricks, just to trick your minds, like sloping the columns inwards or outwards, whatever you name it, right? So it was very subjective. And the problem is we don't really know how to measure it. In other disciplines, let's say some soft disciplines, which are by some not considered science, but I consider them actually science in this scope. Let's say that in the social sciences, right? So the study of how people perceive stuff, we are instead of measuring stuff precisely, we are simply increasing the number of measurements. Even though each measurement is fuzzy, the big amount of data which we get from those social studies is what gives us the precision in the end, right? But the question is it precision or accuracy? But I think it will be precision, right? So, or accuracy actually. Yeah, so anyway, in the end, when we don't know how to do that, like how to measure stuff, we simply collect a lot of things which we hope will give us some understanding, and then we need some tools to boil them down to some conclusions, right? So, and this is the current approach that I have in my thesis. I'm collecting data from the students right now. So I may show you later on, but very easy. We have the first assignment this semester was actually to collect their favorite buildings and just simply give us a couple of keywords or small sentences which will tell us why do they like this particular architecture. And yeah, so then we ask them to send the inputs. We have like close to 100 different buildings, and then we ask them to look through them all again and ask the same question, right? So now the students can actually exchange with different designs, and they can actually pick from all of the the couple of favorite designs. I think we are asking for 5 with we have almost 30 students right now, so it means that we will have 150 responses. Each one of them is something like 3 to 5 keywords. That basically means that we will have something like 500, 700 keywords in the end. And this gives us like a very small step towards getting some data about architecture, right? So this is the first step. Now, what to do next? This is what you will see in this presentation, actually, right? So this is a small introduction of why to do it that way. So Yeah, so and just to finish the introduction briefly, we have so the problem in my thesis is, I mean, the question which I have, the major question, the one question which I asked in the very first place is why AI is present in almost all disciplines around there, but not so in architecture, right? So you may be aware of AI in architecture in the form of genetic algorithms. They are really good for optimizations. Some consider them not AI, but in my definition of AI, which I coined to in my thesis, this is AI. I name AI anything that is capable of replacing or aiding some of your intellectual work, right? So if you have information or data, I mean, this yeah, it's an important distinction, but if you have some data, choosing the right piece of data for me is a very hard intellectual work. And if you have an optimizer which does that actually for you automatically, it means that it replaces some of your intellectual work. That is why I consider that AI. Okay. So yeah, some people will not consider optimization AI, but I do. That's because replacement aiding some of intellectual work. Anyway, back to the presentations. To the presentation, we have a topic which is applications of machine learning in design, very generic, but anyway. You may know XKCD. This is a very interesting comic website. That's some morning coffee. We have, yeah, maybe you can read it. Just give me a second. Yeah. So in this simple comic, you can already see a bit of the things which I talked about. So when you are not really sure about the data you collect, you just collect a lot of it, right? So you have to have this big pile of data to start steering it and trying different things and then figuring out that something might work or something might not work, right? And yeah, that's how people perceive it. But all in all, the tools which we are using are relatively simple. Yeah, some tools are simple to explain, some are actually not. So just to give you a distinction of computer science, AI, machine learning, and then we will talk about supervised, unsupervised. We will not talk about reinforcement learning, but I can just tell you what it is anyway. So computer science is, everything about computing. Not really with, it doesn't have to do with computers. It actually has to do with computing itself, right? So we don't need computers to do computing. This is actually quite important. So we have different fields in computer science. And one of them is AI. Some others theory of computation. There are others like, yeah, I would say probably, I mean, algorithm design is probably in the theory of computation. Anyway, computer vision is as well there as a separate one. So computer vision doesn't have to do anything with AI. It can, but it doesn't have to. We have in the artificial intelligence field, we have a couple of different problems which we want to solve. So NLP, which is natural language processing, it's basically understanding of spoken or written text. And machine learning, yeah, what is machine learning? So machine learning problem is a problem where we ask the computer to learn on its own, right? So that's why it's in the field of problems, right? Our problem is not what machine learning will do, is how to ask the computer to learn on its own, okay? So we have three different ways of asking computer how to learn on its own. One is supervised. That is the one which we'll be focusing on during this course the most. So supervised means that learning by example, right? And I use a couple of different examples to illustrate that. One is, let's say you want to wash the dishes, right? So washing the dishes is a couple of different activities in series, right? There is an algorithm of how to wash properly the dishes, right? So you have to put them in the sink. You have to turn on the water, then put some soap, scrub, rinse with water, and then put on the drying, plate or whatever. So it's a very algorithmic thing, right? A couple of activities which you have to do one by one. Now, with supervised learning, what you do is you simply show the computer this algorithm multiple times, and then it learns it by looking at how you are doing that, right? So you have to write down exactly what you do, show it to the computer, it just learns it by copying your activity. Now, on the other hand, maybe we can, in that context, reinforcement learning is when you just tell the computer that it can either rinse with water, put some soap, put the plates in the sink. You just tell the computer that a pool of available activities, and then you ask it to figure out what is the correct order of doing them, right? So this is learning by trial and error, right? It will try and fail multiple times, but finally it will come up with the right way of washing dishes, right? It will put each activity in order, in the correct order automatically. So then we have unsupervised learning, and this is hard to illustrate it with that example, but with unsupervised learning, we'll have some data, and we will want to look for patterns in this data. So let's say that, back to our biology example, you can actually apply all of those tools in biology, or let's say in anywhere where you collect data. So unsupervised learning with our frog example, right? We collect information about the population of frogs in some area. We write down the length of each frog, I don't know, maybe age, gender, color of the eyes, the radius of the eye or the diameter of the eye, whatever. And we have all of the data, but when you have, let's say, 1,000, 10,000 samples collected from the real world, it's really hard to grasp the overall picture of what this data tells you, right? So as a human, you are probably lost around 100 examples. You just cannot really comprehend them, right? So you can write them down in an Excel spreadsheet and maybe sort by some value, and then see that there is some distinction of those frogs which are, well, let's say below 10 centimeters and above 10 centimeters. Maybe there are two groups, right? And unsupervised learning will help you in that. So it will replace some of your intellectual work, sorting by size, by figuring out automatically how to distinct between those different subpopulations of frogs in the environment, right? So it will tell you that there are frogs which are small with big eyes somewhere, right? There is a population of frogs which are small with big eyes. Somewhere else, there is a population of like dark green frogs with big legs or whatever, right? So with all of those parameters, it will start to distinct those groups, and it will basically serve it to you on a plate. Right? So this is what unsupervised learning wants to do, right? So it's not really learning per se, it's just, you are learning about something. The algorithm is learning as well, but anyway, it's not really comprehending it. It's not really using that knowledge. It just serves it to you on a plate, right? So this is where it's a bit different than supervised and reinforcement, right? We cannot say that it's learning by trial and error or learning by doing. It's just learning by analyzing the data. Okay, so we have, let me just see the next slide. Yeah. So when we have some observations, we can plot them, right? So you can see it that way, like just like here. And with supervised learning, again, supervised learning, learning by example, right? With supervised learning, you will have some algorithm which will take this data and will try to model this data. What does it mean to model this data? It means that we want to have some piece of code which is able to tell us, which is able to reproduce the data, right? When we change its parameters, right? So reproduce or maybe interpolate data in between, right? So in this case, we have this with this series of observations, and that's again supervised learning, right? So when I look at this, I just choose to represent this data as an ellipse, right? And this is my model. Ellipse is the model of the data, right? So yeah, I just placed it there by hand, right? But the thing is that what it tells you now is that there is some order in the data, and you can ask the model what is the observation in some other case, right? So when you have, you know, it's just how many, like that's just 10 different samples, but from the model you can try to guess what would be other observations in the data, right? So what would be in between those different observations, right? And you can ask the model what would be the data in between if I had some, right? Probable data. Of course, it's not exactly the same which we will collect from the real world, but it gives you some glimpse, right? So machine learning in that case is getting that model, right? We instantiate the model. So we create some, you know, model with default parameters. So we have an ellipse here and it has some default parameters. And machine learning in this case is nothing else than fitting that ellipse to the data, right? So we tweak the parameters. We have some algorithms to do that. We'll discuss them later. And we tweak those parameters, and this ellipse just keeps getting closer and closer to our data. So it, in other words, it represents our data better and better with machine learning, right? So learning in this case is just fitting the model to the data, just like that. Maybe before that, we can just talk a bit about neural networks, right? So why would you okay, so this kind of fitting data is usually called regression, right? So you have linear regression where you have a line and you fit the line. You have polynomial regression when you fit a polynomial curve to the data. So it can actually has more, like when you have a line, it can only represent data which is linear, right? When you have a polynomial, it can actually represent any kind of function, right? Polynomials are really good with representing different functions. So you can I'm not really great with math, but you probably can really easily represent a sinusoid with a polynomial. You can represent a line, right? You can fit the polynomial to a line. You can probably get some parabolas or whatever. All of that with just one type of function, so it's polynomial. If you get the equation for a polynomial, I think it has like 4 terms with different powers. Learning is basically changing those each one of those 4 terms, right? So you tweak those numbers. You have different curve, it produces different curves. So it's a good model. So polynomial regression is quite popular. It's just a basic tool. You can do it in Excel, right? You can do polynomial regression with no problem in Excel. You just get a spreadsheet, put some data, plot polynomial regression, choose exactly which degree polynomial it is, and it's up there. Now, neural networks, on the other hand, they are really great because they can represent even more complex data, right? So we talked about the line, we have an ellipse, we have a polynomial which can fit to some really complex data, but it, like neural network beats that by 2 degrees, like how do you say that? Not 2 degrees of complexity, but like it's exponentially better in representing this complex data, right? So it can fit this model way better to way more complex data. You can have super complex data and it will just fit there, right? It will take hours, days, or even months, maybe sometimes. But you can ask the neural network to find the right model for almost anything. So when you see deep neural networks right now, people are using deep neural networks to find a model which will, for instance, recognize different situations on the road, right? Or you can have one which recognizes the postures of people in the image, right? So the image itself, it's an input, right? And here we have data set which has two inputs, X and Y. But when you do that with images, each pixel is an input, right? Usually as a grayscale image, the images are served to the neural network as a grayscale image, but an image can be something like 1 million parameters, right? And the neural network can process it, right? It will be very hard to do that with polynomial regression, right? But with neural network, you can have like 1 million parameters. So every pixel is a parameter. You feed it to the network and you get something out of it, right? So it's not even one degree harder. It's a couple of degrees harder, right? A couple steps harder than just a polynomial regression. Now, in classical machine learning, we will not use deep neural networks. Deep neural networks are quite recent. We'll use just regular neural networks. And this is what I want to focus on during this course. Why? Because this gives you a better understanding of neural networks and just machine learning. Deep neural networks, when I see courses on deep neural networks, they are very abstract, right? So it's way easier to learn about classical neural networks and then switch to deep neural networks than do the opposite. Because when you teach deep neural networks, you assume that people already know everything about just classical neural networks, and people tend to abstract the neural networks very heavily in deep neural networks education, right? So that's why we start with classical neural networks. But there is another reason. So in my thesis, right, I'm assuming that we simply, first of all, we don't have the data. We don't know what is the data which we want to collect from architecture. Second of all, I mean, architecture or design. I mean, I still cannot really decide whether it's only about the architecture or about design. But first of all, we don't have data. We don't know how to measure things. We don't know what to collect and what is really important. Second of all, I think, and this is something which I think that maybe the current methods in AI are just not applicable in our cases, right? It's a very risky statement, right? But I think that it's better to start with very simple tools, apply them to our data and see what comes out. And this will give us a better understanding of what else could be done. Now, why do I think, like, it's a risky statement, like it's very provocative, let's say, to say that other AI tools are not really interesting for architects. But why is that? Why do I think like that? So if you take the best representation right now, which we have, is BIM models, right? So, or parametric models. But let's say, I would say that more information, more data is actually in a BIM model, right? Very easy to prove. Grasshopper code takes a few kilobytes on the hard drive. BIM models usually take like even gigabytes, right? So that's a good source of data, right? And the problem with BIM models is that they are very heavily structured. So you have very raw data about the materials and elements in the building, but the most important thing is not that you have a bunch of materials or elements, it's how they connect with each other, right? And what do they create, and what are the spaces which they create in this composition? So we have, so this is our problem, right? And in this case, the tools which we are talking about, like neural networks, for instance, or unsupervised learning, they're useless, right? With structured data. They are completely useless. There are other tools in AI which might be more interesting, but neural networks per se will do nothing with a BIM model, right? Information. There is no like good way of representing BIM model in a way, like getting the data from the BIM model, extracting it, giving it to a neural network so that it learns something about this BIM model. So this is why I think that there might be a problem with just the tools which we're using for our problems. It's very important to define problems, first of all, right? To phrase, like to write them down. Right now, no one really did that so far. So I try to be the first one. Like, I mean, yeah, that's a bit of a lie. I mean, we'll talk about the problems in AI, but I think it's a step forward from what I want to start with, right? Anyway, back to supervised learning. So, as we said, we have very simple data, 2 parameters, but neural networks are way more capable than that. Neural network can easily distinguish, like letters in an image, right? What we do usually, we simply take different pieces of this image and we look for the neural network response. So if you feed this small image to a neural network, if there are letters, the neural network will, tell you what are the letters. So this is one thing. Yeah, one interesting thing is that R is actually recognized as P, and that is a really good that is a really good example of machine learning because it shows you that neural networks are as prone to errors as humans are. With images, it's very somehow striking that the neural network will make the same kind of error as we would do, right? So P and R are kind of very similar, and the neural network gets confused. Yeah, so that is the bad side of neural networks, that they are really fuzzy, right? But that's also what's their strength on the other hand, right? They don't have to be precise, but there is a sweet spot somewhere. Then a good neural network will be fuzzy enough so that it can generalize, so it can apply its knowledge to different cases. But on the other hand, if it's too fuzzy, so too imprecise, it will make mistakes just like that one. Okay, so unsupervised learning. As I said, unsupervised learning, supervised learning, those are 2 different things. But unsupervised learning is where we have a data set. We want to distinguish 2 different groups. And this is called clustering in this case. We have other unsupervised learning tools, methods, or really applications, let's say. But this is one of them. This is the most common one. We simply want to find out different groups. Yeah, actually, this grouping is as good as any other grouping, which would cut them in half. There is no real 2 groups in here. There are no real 2 clusters in here. I just drawn them manually. So it's actually not really a good clustering, right? And finally, reinforcement learning. Let's skip that one. This is where I want to really skip. Maybe I will just show you what reinforcement learning can do, but I will not get into details of how it works. Can I? Yeah, it runs. I'm not sure if you can see it, but reinforcement learning is basically, as I said, give the robot a space of possibilities, right? So this is what this guy does right now. It shows the robot that here are all the movements which you are able to do, plus it gives it some, range around those movements, and then figure out how to put those movements in the right order to flip the pancake. Now, what is great about reinforcement learning compared to supervised learning is that it starts to work really, really soon. So you can see it's 10 trials and it's visibly better. With supervised learning, anything takes tens of thousands of iterations, right? Supervised learning is really slow. Reinforcement learning can be really fast, just like that one. but it has to be really engineered properly. So reinforcement learning, I would say, it's more challenging algorithmically than supervised learning. Supervised learning in the end is all about figuring out the right parameters. With reinforcement learning for the neural network, like the size of the neural network and the architecture of the neural network, with reinforcement learning, the problem is that you're playing a game with the algorithm, right? And the game is cold and hot, right? Or warm and cold, however you call it in English. It's basically you tell the algorithm how close it is to the right solution, right? Or and the right solution is usually you don't exactly know what it should do. If you knew, you would tell it how to do it exactly, but you can see the outcome, right? So in this case, it's a flipping of the pancake, right? So you tell the robot that you were that close to flipping the pancake, right? It went high, but now you have to rotate it, right? So it went high, so you were better than previously. And the robot will just go and continue exploring all the combinations of movements, starting from that one which you told it was good, right? So it's basically navigating it through this problem by telling it how good it is in performing something. Uh, and this is really hard. Like telling the robot what is good and what is wrong is really, really hard. Uh, you may be aware, maybe we'll talk about it a bit later because this is, I mean, it's not really the scope of our course, but I think that there are some really interesting examples of reinforcement learning going wrong. And this, if you know a guy called, no, if you know the Computer Fire channel on YouTube, they are talking about that in the context of general AI. So all-knowing AI going bonkers and basically destroying the world because of using reinforcement learning and incorrect tasks for the incorrect boundaries for the reinforcement learning, right? I mean, the classical example, just to maybe we'll just diverging off, but there's just so many interesting things out there. You have like when you have general AI and you tell it nothing about the world other than how it works, but you will not give it any ethics. It can, for instance, kill all the people to collect all the post stamps, right? So you give it the task like, please collect me a nice bunch of post stamps, right? And the reinforcement learning like algorithm without any boundaries, so general AI with no ethics, no knowledge of what is right or wrong, will simply, well, use uh, the least amount of energy, for instance, to collect all the post stamps. So it can do a lot of different things, right? It can, I mean, maybe destroying the entire humanity is a bit too much energy, but for instance, hacking, uh, a print shop, right, which makes the post stamps, and then printing the post stamps on its own, that's something which would be within reach, right? If assuming that the print shop is actually connected with the internet, and the general AI can write code and can hack the code, it would be able to do that. Just hack the print shop and just print it on its own, or print money, right? Uh, Induce a huge inflation, but then print money and then buy all the stamps for you. So if there are no boundaries, that's what reinforcement learning can lead to. But of course, that's a huge exaggeration, right? Usually, maybe we'll see that a bit later. Usually, there are like, if you try to teach the computer how to play a game, it will find all the little tricks to fool the game, right? To win the game in very unconventional ways. Anyway, so yeah, when we have the SpaceX with flying downwards, right? So they are going downwards and they have this rocket. If I were an engineer at SpaceX, I would really like to. I mean, I'm not sure how they do it, right? Of course, and I'm not rocket scientist. But if I were a person there, I would really like to try reinforcement learning in this case, because a classical example of reinforcement learning exercise which computer science students do is balancing a stick, right? So this is a very common like home assignment for the students to make a robot or make an algorithm for a robot which has 1 degree of freedom. So basically it's a rail with a motor and have a stick placed on top of it and simply move left and right and balance the stick. Like, so when it wants to fall off, the robot needs to catch up and just put it back straight up. And this is very common with SpaceX and the rocket. They basically have the same problem. They are having the jet here, and then the rocket tries to do everything to fall. So they have a lot of different actuators, like actually small, not really jet engines. I think they are, anyway, I think they have pressured gas or something like that. So they can fire it in different directions to keep the rocket straight, right? So reinforcement learning, if you were able to model this complex environment with all the turbulences and airflow and the complex behavior of the interface of the jet engine and the ground plane, right? This is where everything really happens. If you were able to model it on a computer, technically the algorithm to correct the position of the rocket could be totally done in a computer, right? So you could technically train the reinforcement learning on this very complex virtual model and then release it and just have the rocket land, right? It's super hard, right? But it's technically possible, right? But it's hard. Yeah, probably not done that way. Probably they do it. I think that they have some really good engineers. I just think that they have different methods for that. Not sure exactly what are the methods, but I wouldn't trust reinforcement learning on that. Anyway, so I wrote a paper last year, actually this year, about why AI is not in architecture, right? So what I did, I analyzed like 400 papers. I collected papers about AI in architecture from a couple of conferences. So from the early 80s, the first ECAD conference was 1983. ECAD is the biggest computers in architecture conference in Europe, and is a sister conference of Acadia, SIGRADI, and some other conferences in Asia. So they have a huge database which is called CommunCAD. And this database has a lot of PDFs, right? So you can search the PDFs, and I searched those PDFs for anything that could relate to AI or knowledge representation, right? So you know why right now, why? I'm interested in both knowledge representation and AI, because knowledge representation is crucial for successful AI. So, and I found this paper, and this really inspired me to write this paper, which I ended up with, which was basically a list of what is wrong with the current AI research and why are we not progressing since 1901. You can see that this paper is a workshop report from John Garreau. This guy wrote like hundreds of papers about AI in design and has a lot of PhD students. Like, he's really, really productive. Probably, yeah, ultra productive. Anyway, in 1991, there was a workshop on AI in design, and they wanted to figure out what are the problems for AI in design. Yeah, and I made an update of the list, and it seems that we have only a couple of those problems solved with AI. The rest is just blank. So again, we'll just go through the list quite. Yeah, I mean, yeah. Let's see how much time we have. I think we are good. So we have representation and design, right? So I'm quoting like those sentences down there. There are just quotes from Garreau. So what is that the designer knows, and how do we get the computer to know it, right? So again, I'm just linking back to the introduction, right? If you have an environment with frogs and you make some biological study, you ask about the length of the frog, the size of the eye, the color of the frog, gender, whatever. And then that's your knowledge, right? This is what the designer knows. And how do we get the computer to know it? That's another thing, right? So what part of reality do we want to model, right? The model in like the definition of a model is basically copying some subset of reality, right? Which is interesting to do something, right? So if you want to model, let's say, turbulence patterns in some building environment, right? You are not really interested in the population which lives in that area, right? You're interested in the shape of the buildings, the winds, which is usually, the direction of the wind, which is usually blowing there. So it's really important to choose what is the subset of reality which you want to model. And with architecture, that's really hard to figure out. Yeah, so we can say that we have one way of representing design is to just represent everything, right? So we have 3D scans. The problem with 3D scans is very unstructured, but that's actually good for AI. But still, for us as architects, we would like to know what it is actually in that scan. Now, the second problem was design semantics. So coding and decoding. So once you have once you decide what do you want to get from the environment, like what is the data which you want to collect, you have to know how to encode it, right? And again, this is a paper from 1991, and this problem has been actually addressed, right? We have parametric models and we have BIM models, right? So we know what is the data we represent, and we know how to code and decode it. That's good, right? So those two problems are kind of addressed, right? Far from perfect, right? BIM, as you know, is not perfect, right? Try to export the IFC model from Revit to ArchiCAD, you will know what I mean. So on the other hand, we have parametric modeling. So BIM model is one, parametric modeling is another one. What is nice about parametric modeling, but also super hard to use with AI, is that with BIM models, we are giving it some raw information about geometry, right? So what are the materials, what is the function of it, whatever, but you give it the end product. With parametric modeling, we're able to tell the computer how to build things, right? How to design things, right? So we are not informing the computer about the end product, we are informing how to create the end product. So we are teaching it procedures, not just raw data. That's really like it's in my 1 second. I just need to mute the phone. 1 second. I'm sorry. So we have. Let me mute this guy. Yeah. So we have. Again, so we are not teaching the computer about raw data. We are teaching the computer about the procedures which we use, which technically, I mean, it sounds amazing, and it is amazing, but still, it's like we cannot really use that. Right? There have been, of course, we can use it for optimization, right? Parametric models are great for that. And I talked with some, like engineers, and they told me, like, look, parametric modeling in engineering is old school, right? We've been doing that for years. Now you're just doing it on a computer. But when you design a bridge and you have bracing, you have different thicknesses, those are the parameters, and we've been doing that all the time. So architects do the same right now with let's say Grasshopper, for instance. And it's nothing new in building industry, but it's new for architects. And I lost my thought here. But anyway, parametric modeling is great, but Yeah, but we don't know really how to use that, right? So of course we can optimize. Like if you imagine a bridge, you have different cross sections and you just optimize the cross sections, right? You analyze what is the structural efficiency and you optimize that. That's one application. That's why, I mean, genetic algorithms are actually well studied in architecture. But when it comes to architecture and design and qualities of design, I mean, it doesn't give it really, like, it's not that so easy, right? So there have been different attempts. John Harding is one guy from Bath, one really interesting researcher, wrote a couple of really interesting papers. And he was exploring this way of playing around with graph representations of graph coding, right? Visual coding, where you take the graph, and instead of manipulating the parameters in the graph, you manipulate the parameters in the graph as well as the graph itself, right? So this is called Cartesian genetic programming. Cartesian because you have this graph and you have this Cartesian plane where you put the graph on, right? So this is one way of modifying this. It was one attempt. He wrote a couple of papers about that. He showed what it can do. And that's it. I mean, it's really great. It's really interesting and it's really cool and geeky. But the problem is that we don't really know exactly how to use it. It's really hard to set up in the end. And the problem with architects is that they try to be creative. Like, so they try not to reproduce something, what they've seen so far. So they try to come up with something brand new every time. And this Cartesian genetic programming, when implemented in a very simple way, will produce kind of similar shapes in the end. And it's also really hard to produce like a really good parametric design. Anyway, so parametric modeling, 90s, Waterloo, London, that was the first building made with parametric modeling. That was still, I think, designed with microstations, so everything was scripted, but still it was a parametric design. Now, problem number 3, that's we are like nowhere near addressing this problem. So problem 1 and 2, representation and encoding and decoding is there. We've been addressing that for the last 30 years, right? So Waterloo is 1994, I guess. And parametric modeling was in very like early stage in architecture, but it was there in computers, right? As you see in the building here. Inference in design is like, we have no idea what to do with that. So let's start with a quote. In design as elsewhere, the content is often much more than has been expressed directly, right? So as a designer, you make a decision and you have this kind of intuition what it does, right? You have a purpose in decision. So let's make a building taller, right? And by making it taller, you automatically know, like, there is this notion of tacit knowledge, right? So knowledge we cannot really address directly, but it's there. And we use that all the time in design, where we make a decision, but we know that it influences way more than just the height of the building, right? Yeah, so this is where the content is much more than that what has been expressed directly. There's always some context of that content which we are doing. The height of the tower is just one example, but you can put any example here, right? Like, yeah, whatever, any parameter of the building, or any parameter of design, or the shape, the dynamicity of the shape, or whatever. This is not only influencing the volume of the building, but also all the other qualities. What are the qualities? That's a great question. A good example of understanding what is that inference is this game of Hanoi Tower, right? So if you know the game is to move the blocks from one peg to another. So it goes like that. It starts in the top left and it ends up here, right? Step by step. So when you have like those IQ tests, right? And they show you 2 steps and you're asked about the 5th step, right? This is exactly that. If I were to show you this Hanoi Tower by, I think, the first 4 images and the last one, and I will tell you to fill in the gaps. If you're, let's say, I would say above average intelligent, you would be able to figure out what are the rules from the first 4 images and then get to the 5th image, right? So the rules are, just to tell you, the rules are that you can only place a block on another block if the block which you're placing is smaller than the one which you're placing it on, right? So you can see it actually here, right? It's placed here, it was placed here, like this block can only go on top of this one, but not the other way around. And the task is to get from here to here, right? I don't have to describe you all the steps. I just describe you the first 4 steps and then the last one. It's up to you to fill in the gap. And this is inference, basically. So we understand that there is something and there is something, and then it connects, right? So there is, yeah. So this is one example. Probably not the best one, and probably technically I'm a bit wrong here, but I think that this is just a good intuition of, yeah, of what do we mean by filling in the gaps of the things which we don't really have explicitly stated. Yeah, then problem number 4, this is surprisingly well studied. Why? Because we have parametric modeling. Combinatorial explosion in design is as soon as a system deals with what, I mean, I'm just quoting here. So as soon as a system deals with what could be done, what could be, then it could go indefinitely. So as soon as you have a complex parametric model, you have a lot of solutions. So we say that when we model parametrically, we don't create one design of a building, we create an entire spectrum of designs. This spectrum is usually called solution space, right? So every parametric model is actually a solution space. And by using Grasshopper, you just pick one solution from that solution space. And with every new parameter, the solution space expands exponentially, right? So let's say you have one parameter, can be either 0 or 1, you have just 2 solutions. With 2 parameters, 0 and 1, again, true or false, you have 4 solutions. With 3 parameters, you have 8. That's exponentially growing. Now, this is just with one bit of information, like true or false. What happens with a slider? Let's say you have a parameter which can go in a floating point, 0 to 1, but it can go with a step of 0.01, right? So 100th. Then you basically have 100 different solutions just for one slider. With 2 sliders, you have 10,000. And with 3 sliders, that's, I think, 1 million, right? Exponentially growing. Each new slider will give you an exponentially bigger solution space. That's what we call combinatorial explosion. So David Stasiek, really smart guy, Letter Thompson, my former boss, they wrote a paper about exactly about this, and how to deal with that in architectural design. And there's a really great paper on unsupervised learning. So they are using k-means clustering to battle the combinatorial explosion. So they created this model of this arch. I'm sorry, on this arch, like a complex composition of arches. They're actually simulated, as far as I know, in Kangaroo, and then they build them in physical world as well, just to match the simulation with reality. But anyway, they have those really interesting shapes, and then the Kangaroo, or actually the inputs for the model, are the positions of the tips of those arches, right? So where they are placed on the ground. And I think that's it. I'm not sure if the number of arches is fixed or not. You can read it in a paper. Anyway, they have a lot of different ways of arranging those arches, and they simulate them, and then they use k-means clustering to figure out, okay, so you have this huge solution space, and you know that the solutions which are next to each other will be probably quite similar. So if you change one parameter just slightly, it will not dramatically influence the design. So there are areas in that solution space which will have designs which are similar, but not exactly the same, but similar. Then there are some other areas in the solution space, right, which could be also similar to that area, right? So maybe there are 2 patches in this hyperdimensional space. Let's say we have 10 sliders. That's 10-dimensional solution space. In that hyperspace, you can have two patches with the similar designs. Without tools to analyze this solution space, you're basically blind, right? You cannot do it by hand. You cannot learn about the possibilities of your parametric model if you are not using some AI in this case. The AI which they used is KB's clustering, very easy algorithm. We'll not learn about it, but I will show you how it works anyway. Just a quick one. So it's basically grouping the points by proximities, nothing else. And then we have, we have those very high dimensional points. We group them by proximities, more or less. And then we have points which are close to each other, and they usually represent something more complex, right? So in this case, they represent those complex arches. And you can see each column is this cluster of similar solutions from that solution space. They are similar, but they are not exactly the same, right? So they've been grouped by different parameters. You can group them by input parameters. So let's say the input parameters are the initial positions of those end tips of each arch. But then there are output parameters as well. So for instance, how many intersections emerge from that initial position, right? Or what is the total height? That can be also a parameter used in the clustering. So they extracted something like, I think more than 18, maybe 30 parameters, which describe those designs, and they just wanted to test if it's actually working. And you can see that, I mean, in my opinion, it works. You can see that each column has actually different designs, but they are similar to each other. And the similarities are not trivial, right? Because it's really easy to measure a square, to have two squares and tell that they are similar because they are both squares. But with a complex design, that becomes much more complex, and actually measuring those differences is hard. That's the point of this paper, actually. So you can read that paper. There's a citation here, right? So you can look it up here. It's actually on Kuminkat as well. Very nice. Another way of dealing with, and this is what we will be doing. So another thing with combinatorial explosion is mapping. So let's say that your solution space is huge. You have some parametric model, and you have some solution space, but you are not really interested in all different quirky designs. You're only interested in a couple of different designs, and you want to only move in between those designs. So if you have 100 sliders, you know that you have maybe 4 different designs where those sliders work for you, right? So you select them by hand. So this is where those yellow selections are from. They are selected manually. But then in this case, we are interpolating between those designs. So basically creating a subset from that solution space. Like imagine selecting pixels in Photoshop. That is basically selecting subsets designs from a vast solution space. Now, why is that interesting? Is because it creates this really interesting map, but also it reduces the dimensionality of solution space that we'll talk about later. And again, for instance, if you were to use optimization, right, and your initial model is the one on the left with all the different ellipses, the optimization might come up with a solution which is not really interesting for you from some standpoint, right? So for instance, you might not like the shape of it, right? And you want to pre-select some solutions and then let the optimization run only on that selection, right? So you know that whatever comes after optimization will be something which is somewhere in between the things which are interesting for you as a designer, right? We'll do that. We'll do that. This is again John Harding. We talked about him. John Harding did that with self-organizing maps. We will be doing that with autoencoders. To be honest, self-organizing maps are actually faster and fun. Autoencoders are just fun. They are not really great, but they are doing the job, so that's important. Slower than self-organizing maps, certainly. Now, we did a workshop a couple of years ago in Dubai with students, and we used autoencoders. Basically the sub-selection of solution space to figure out what it could be useful for. And we created this model of a parametric bench where it could have, like, as you see, it's a range of different solutions. and we wanted to illustrate what are the possible solutions. It's actually just a small subset of all the possible solutions, but still it shows you what are the possibilities out there for this parametric design. And the students actually mapped the different solutions from this map to different locations in the city, which was quite a speculation, but that's what designers do, right? Another one is this one. Let me see if I have the animation. Okay, I have the animation. So we have another one is this one, where each of those compositions is actually a separate parametric model, or actually it's the same parametric model with different solutions, right? So for each of those compositions, we have, I think, 21 parameters, right? So it's the dimension of each of the 3 boxes, that's 3 parameters, location of the map, which is 2 parameters, and the color, which is just a hue. So it's another one. So we have in total for each box, we have 6 or 7 parameters. Oh, and the rotation, that's another one. So we have 7 parameters for each box times 3 boxes, that's 21 parameters. Now, again, 21 parameters, those are the selected compositions. I just wanted to make a map, so interpolation between them. And this is how it's done, right? So you can see those are the 8 selected solutions, and now this map is being created by autoencoder, right? So autoencoder simply places them on the map and then interpolates them, right? So this is a slice of this huge solution space, right? With 21 sliders, you can say that, with 100 different possibilities for each slider, right? So we discussed that from 0 to 1 with a step of 100. With 21, you have 100 to the power of 21, right? That's the number of possibilities which you can have. With that one, you just limit the number of possibilities, but that's what you want to do with combinatorial explosion, right? You want to limit the number of possibilities. That's where you have too much information, too much data. I don't know why is it here, but oh yeah. So another way of dealing with combinatorial explosion is to use optimization, right? So we discussed already, 1 second, let me go back. Just need to remind myself what we discussed. K-means clustering, that's basically clustering, figuring out what are the areas in the solution space. Another one is selecting a subset of the solution space. And another one is finding the point in the solution space which is satisfying our requirements. 3 different ways of dealing with combinatorial explosion, right? Probably the best studied AI problem in architecture right now. And in the bridge, this is a project which I've been working on 4 years ago right now in CETA when I was still there. So we had the bridge and we optimized the bridge. Basically, we optimized it for the structural performance, but also like seam proximity. And as you can see, there was another one which was, let me see, what was that? Qualities of common areas. So whoops, again, once more, 1 second. Not sure why is it, okay. So the thing is that, let me pause this animation here. So the bridge has 2 layers, and the structural engineer, in that case, it was actually Ricardo Lamagna, really smart guy. He told us that when you have 2 layers, because those are 2 metal sheets, right? And you have different panels, you have to move away the seams from 2 layers as far away as possible, right? So when you have, oh man, I'm in the need of paint. Maybe it's not really that important. Anyway, maybe I can just draw it here. So when you have this seam on this layer, it's good if the layer below it doesn't have a seam here, but it should have a seam here, right? So it works more or less like bricks, right? They have to have the bricks. You cannot put the bricks on top of each other like that because the seam is where the weak point. It's kind of similar with the metal sheet panels where you have the seams. This is the the chintzy region, right? It's just not really efficient structurally, right? So we wanted to move away the seams from each other, and this is what seam proximity means. Structural performance, that's easy. Karamba simulation, we measure the deflection in the middle when 100 kilos are placed on the structure. And the qualities of common areas is that if you take a look here, where is it? Here, you can see that those indents in the panels are actually what connects those two layers, right? So each panel has some indents and they are just, mounted to each other like that in those points. Maybe I can show you here, right? And here. So you want to have as many opportunities to make that connection as possible, right? So that is where the measurement for quality of common area comes in. The bigger the common area is, the better, because we can place more connections between the layers in those cases, right? So those are 3 different measurements to take. And then we have some fitness, which is basically a combination of those parameters. And then we see that in the end, we end up with this very particular design, and this just to illustrate what are other designs. So this is another way of dealing with combinatorial explosion, probably the most popular right now, right? So if you have any problem, you will just optimize it right now. Quite common. Not sure if this is really a good example here. I mean, this is just a building where they use k-means clustering. So the thing which David Stasiuk used with the arches, but they used it to optimize the panels. So they found panels which are similar in size and in shape, and they averaged them. So instead of having 20,000 different parameters, 20,000 different panels, I think they ended up with something like 100 different types of panels, but it was way easier to assemble, right? The guy, I was actually Prague 2012, there was a ICADI conference, and the guy who worked on that was telling that the problem isn't really cutting the panels, right? Because we can, with a laser cutter, we can cut whatever shape, and no matter, like, if it's 10 copies, 1 copy, it doesn't matter. The problem is with the assembly, right? So if you were to have 20,000 different panels, then it would be, the drawing for it would be a nightmare. Organizing those panels on the construction site would be a nightmare. With 100 panels, 100 types of panels, you basically have a 10 by 10 grid of panels, and you see which one from 1 to 100 you have to take and place on the facade, right? So it's way easier to organize, way easier to instruct people how to do that, and the drawings also become much easier, much simpler, right? They can be color coded, and you can see that from here to here, you put that panel in that orientation, right? So that was the idea behind that. So they basically took k-means clustering, they took the shape, they took like 30 different parameters actually from each hexagon, 32, 37 parameters, and they clustered it. They used Excel for that with VB. That's a very slow one. Took a couple of hours to cluster that in the end. But it's yeah, so they ended up with 100 different families. They show there is a really good issue paper on that. There is like a PDF which you can look. They are actually showing exactly what they are doing there, which parameters they take from panels, and what are the other options which they generated, because they generated options with 10 families, 100 families, 1,000 families, and so on. So, and they analyze what are the gaps, what are the parameters, how they influence the gap size, and so on. Yeah, in the end, it's also kind of combinatorial explosion, right? 20,000 different solutions. Now, problem number 5, barely touched. So, indexing in design. The more knowledge that is coded into the system, the harder it is it is to find what is useful. So, yeah, so you have a library of solutions or a library of whatever data, how to find the one which is interesting, right? And this is where Autodesk did some steps with designing graph. They start with a neural network which is able to recognize 3D shapes, right? So they input a 3D mesh, and they have a neural network which tells you what is the shape. Like, it's a classifier network. It classifies the shape into different classes. And they use a very smart approach with that, because Yeah, anyway, it's not as easy as it sounds, right? It's actually very hard to get the shape to be represented properly. So they have this neural network which can recognize different shapes. So understanding that this slide will show you that there are 5 different plates. They are similar, but they have different thicknesses, different sides, and so on. But all of them can be classified as some mold plate or cavity plate, right? Because of the similarities in shape. So once you have a network which can tell you what are the similar shapes, you can actually create a graph, right? So you can, for instance, you can create different graphs, but you can create a graph of elements which are connected to other elements in different assemblies. So when you have fasteners, and there is with some power transmission elements, you can see that those 2 elements emerge often in some particular designs and not in some other designs, right? So power transmission will not probably be used in a bike, right? There are gears, but they are not like that, right? Different shapes. So you can have this very, very complex graph of elements, and you can basically point an element and ask the graph or analyze the graph to understand in what context this element emerges in different designs. And you can do quite a lot of that, right? Like you can do quite a lot of different tools using that, right? So for instance, you can say that you could do like a search engine which tells you what other designers did in a situation which you are in, right? So you can say that I have this element and this element is my design. I want to see how to connect them together based on some other designs, right? So you can search this graph for a similar combination of elements, and it will just show you that other designers solved that particular issue in that particular way. That's the theory. Now in practice, I have no idea why, but they shut down this project. There was actually a design graph website where you could, it was actually, I'm sorry, it was actually a plugin for Autodesk, how do they call it right now? They have like a cloud, right? So the Autodesk has some cloud where you as a user can store your drawings and models. And design graph was at some point, it was available to search your 3D models and create a design graph for you. So you could take the, like, let's say, if you search fastener and you see all the assembly which have fasteners. The important thing is that the neural network was responsible basically for tagging the elements, because when you model something in 3D, I mean, you can expect people to write down what are the elements, but they usually don't do that, right? So the neural network did that stuff, right? The neural network was responsible for telling you what the elements are and tagging them, and that was the crucial part. And the design graph is kind of an obvious thing which you could do with that kind of neural network. But anyway, the project is not available anymore, but it was 2015, I think, when they did this. Yeah, so another problem. So indexing, like, just to conclude, it's not there. Like, we have no other approaches than that one. I mean, nothing which I found so far. Anyway, dynamic modification, learning and design. So again, quotation. In design, unlike the fields in which rely on deductive processes, getting the same solution twice for the same problem is considered a failure. Every architect tries to be original, right? Even if you have the same location, like a very similar location for your building, as an architect, you would never do the same building twice. I mean, assuming you are an ambitious architect, right? Some people will just copy paste the same building everywhere. But good architecture usually is non-repetitive. Like, we consider good architecture non-repetitive. I mean, there was of course the the Plattenbau, the communist blocks, basically prefabs, which are all the same everywhere. But I mean, why they solve really a lot of problems, especially in East Europe. The 50s and after war housing problem, the crisis basically with the housing and trying to get the people to this. I mean, trying to get the people to the city. That solved that problem. But on the other hand, on the urban scale, those settlements are often, well designed, but on a single building scale, they are usually failed, right? So there was even in Poland, we had even this. How was this guy? The prime minister going to one of those apartments in a new block and telling the builders to build them a bit bigger because it's a bit too small, right? So there are, of course, design failures like that. But anyway, in some cases it works, in other it doesn't. And currently, I would say that architects tend to be original and try to build every building different, right? So very local, very context aware. So far, nothing has been done in that case. Like, I could not find anything about that currently, right? Why? I think it's because all the previous problems, like representation and so on, those are the problems which we addressed, like the combinatorial explosion, parametric modeling, like encoding, decoding, that is addressed. But dynamic modification, learning and design requires a couple of different steps to be solved first. That's why I think we are just not there yet. When we will solve that, I'm not really optimistic. I hope in my lifetime. That's my hope, because I mean, parametric modeling, right? That's 30 years old idea in architecture. In engineering, that's 100 years old idea, if not 200 years, right? But in architecture, that's 30 years it took us to get to a point where we have a good parametric modeling tools. Dynamic modification much more complex. I don't think that it will be solved that soon. Yeah, so learning, while you're designing, you want to learn things. Now, another problem, generalization in design. So the ability to draw conclusions from disparate cases, from different cases in a single case, right? So basically generalization, what it means is that you have some knowledge and you understand that this knowledge is useful in other contexts as well, right? So you can understand that this context is similar to that one, and some part of the knowledge which you get from one context you can apply in this other one, right? So when we say that something generalizes well, it means that what we know will work in some other cases as well. And I mean, this is a very, I'm stretching it a bit here. So in the bridge project, we actually, in the end, by the very end, we still had some time and budget in the project. So we wanted to experiment something with some more machine learning than just optimization. And we did a 3D scan of the panels with very high precision and accuracy again. And we wanted the neural network. Okay, so the problem with those panels is, do I have it over here? Yeah. So the problem with those panels is that when you do the incremental sheet forming, that's the, it just is a tip, metal tip and ball. I mean, ball and tip, which is sliding on the metal, but you can see that it's all wobbly, right? So when it extrudes this metal, the metal has some spring back. So let's say you want to extrude it by 2 centimeters, but because of that elasticity of the metal sheet, it's some of that force is actually not transferred to plastic deformation, but to elastic deformation, right? That will be always case because plastic deformation is further down the line, yield line, than the elastic deformation, right? First we have elastic, then we have plastic. So you know that if you want to get the plastic deformation, you have to go through elastic deformation first. So some of the energy which you input will always get back. So we have to fight that. And yeah, so how do we do that? So first of all, we asked, what could neural networks do for us in this case, right? Because we have cases, right? We scanned those panels. From each panel, we took a couple of 100 samples. It was actually quite a lot of samples, different orientations, different parts of the piece. We took like small depth maps, right? Like grayscale images with 81, like 9 by 9 pixels, which measured what is basically the shape of this local feature. I think it was like 5 by 5 centimeters. And we took a parameter which told us how far is it from the edge, because there is a mounting rig around that, which holds the panel, right? So there is a MDF board with a cutout. You put the metal sheet in the cutout, and then the robot does its job. But then the metal sheet is much stiffer. So we measure how far the point, the forming point is from the edge, and also what is the local feature. So if there is already something like here, like a slope. The incremental sheet forming is actually cold forming. So what it means is that the metal is actually stiffer. It actually changes the crystal structure of metal on, I'm not sure if it's atomic level, it's a bit higher. So it's a bit larger. But anyway, we measure the crystal, we change the crystal structure by pushing it, right? Cold forming. When you have a wire, like another example of cold forming and what it does with the metal, and it actually affects it greatly. When you have, let's say, a soft steel metal rod and you bend it, at some point it actually becomes harder, right? And it can break, it will be brittle. That's because cold forming makes the metal harder, but also more brittle. So that's why we also wanted to have not only the distance to the edge, but also the local feature, right? Because technically it should affect the local response of the local spring back. So we had 10 panels. And I think we used 8 of them to teach the neural network what are the input-output parameters, what is the input toolpath, what is the output shape, and then we tested against those other 2 panels, right? And to our surprise, it was quite precise in predicting what is the output shape, right? So you have some input geometry which you generate a toolpath on, and then you have some output shape. So when you have that pairing, you can teach the neural network. And then when you take away the target, like the target geometry, you can ask the network, okay, all of this stuff about the other panels, tell me what would happen in this panel. It was actually quite precise. So tested it and it worked. Yeah, it's a good interesting stuff. So it was, yeah, so why, okay, so one generalization is that it's a stretched, right? So it's a bit stretched here because we were able to reuse some knowledge from some panels to design some other panels, right? That is a bit stretched. Also, it's closer to material science than design, if you ask me, but that is how it is. Nothing really more in generalization in design. Again, I think it's because of all the other problems not being solved yet, or at least approached at some point. Situation recognition in design. And this is one interesting paper where they took a neural network. I think do we have some slides? Yeah. So again, we start with the quote from John Gurra: much of the interest in conceptual design lies in the emergence of newly recognized situations which were not produced intentionally, but extensionally. Whatever. So we want to recognize the context, right, of our design to understand what is it about, right? And this paper just shows us one of those approaches. I consider it an early approach, but still it's an approach in this direction to solve this problem. And they used a neural network, I think, which was a convolutional neural network. We'll talk about them a bit later. Convolutional neural network work with image, right? And they tell you, in this case, the neural network did a classification. So they had different types of spaces, and the neural network told us what is the type of a space around some point, right? So they take the panoramic depth image. This is what we see here. Those are panoramic depth images of a particular architectural space, like here, for instance. This is what they show. And then they are able to tell, like the neural network is able to tell what is the exact, I mean, not really exact, what is more or less the type of a space which it shows, right? Now, yeah, so this is one approach. I'm not sure where it's going, like where it's heading, but it's an interesting direction, and I think that this is what is nice about it is that it's very simple, right? But it gives you an like a basic understanding of something which is a bit more complex. So what I mean by that is that the algorithm itself is trivial simple, but when we talk about measuring stuff in architecture, I think this would be the one way to go, right? So as I said, again, we go to biology, we have a frog, we measure the length of it, whatever, weight, color, and so on. We can measure it. And I think that this could be one way of measuring stuff in architecture, right? So we are, as humans, we are very prone to subjective opinions, right? Subjective judgments. And if you have, let's say, 100 different designs, and you have to tell me what is the type of each particular design, by the time you reach the 20th design, you are so bored with all the designs that you don't consider them innovative anymore. Right. So let's say you say that some designs are original or innovative. By the time you see the fifth one, you're probably going to be so tired because of that it's gonna really influence how you judge it. So I think that this could be a good direction to make some evaluation techniques, right? So evaluation, which means like tools to measure architecture. I think that this could be like a very good direction to follow in this case. And I think that at some point I will also want to do that as well. Now, problem 9, creativity in design. And yeah, this is the most like philosophical problem, let's say, because we don't even know what creativity is, right? We can define it in a few different ways. And I'm not a philosopher to tell you what are the ways, but I can expect that there are a few different ways. The ever-going question of if the computer is creative or is it the person who created the algorithm, right? And it's exactly the same here. We have a cycle gun, which transfers the style. You probably heard about style transfer, where you can take a picture and paint it like a Cézanne or Van Gogh here, right? And this is done by using some really complex deep neural networks. But the question is, who's the creative person here? Is it the algorithm or is it the person who created the algorithm, right? And I think I have a strong opinion on that it's the person who created the algorithm who is creative, and the computer just does what it does. I don't think that the computer has any slight input here. I think it just repeats what you taught it to, even if it's a complex function which we don't understand. I don't really agree with that being creativity in computers, right? I have no idea how to make a computer creative, right? I have not the slightest idea. Like I'm coding for a couple of years right now. I never did a piece which was creative on its own. I was creative with the code, but the code itself was never creative. A good question for you. Maybe you have some idea, like what would you create? At what point would you consider the computer being creative? Even stretching it to the future. Artificial general intelligence, AGI, right? You have a computer which is smarter than you. Is it creative when it's painting? Is it creative when it learns everything about all the paintings in the history of mankind? And then based on that, it uses that knowledge to paint new paintings? Is it creative? That's a good question. And then again, I mean, if we want to be a bit philosophical, some people think that that's what humans do, right? So we are not really ever creative. We only repeat what's been done so far. We get inspired and we just repeat it. A very complex algorithm on how to repeat stuff with being considered creative, but still, maybe someone will understand this as creativity, maybe someone will not. And that's, yeah, I'm not a philosopher, not the right person to ask, but I mean, this is certainly not an easy question to answer, not an easy problem. We can fake creativity, just like here, but I don't think that we can ever be creative with computers. Benjamin Feldbrich did some cycle gun. Is it cyclogun? I think it's cyclogun as well. Style transfer between Rhino models and sketches. So he did some sketches and he wanted to sketch the Rhino models just as some architectural sketches. This is how it works. You can look at the Vimeo as well. Just Google Benjamin Felbury. I think that he will. He has. I have no idea what's going on with him, but he moved to Australia and did some more of that, I think. And if you Google like creative AI, this is what you get. Cyclogun again. Now the question is like style transfer or just like whatever transfer. Is transforming faces to ramen, just as you see in the bottom, is it creative? Again, I don't think so. I think that the person who invented that was creative, but I don't think that the algorithm is creative on its own. I mean, maybe I'm a bit too purist about that. I have no idea. And finally, we have problem number 10. And this is something which was kind of approached already. And I think that this is really important. I think this is the next step to do, which is natural. Like this step emerges naturally from what we've been talking about so far and where we are at currently. So the evaluation process in design include not just the evaluation of the technical performance of the design artifact, but also an assessment of its social ethical value. So this is exactly what I'm trying to do right now, like at this point of my PhD. So we have this is actually, I always forget to name the person who is responsible for that image. That's actually Robert Verlinger. He's a structural engineer, very smart guy. A couple of plugins, Octopus, one of them. Worked with Karamba as well. Not sure if he coded Karamba. I can never tell if he's teaching Karamba or also coding, but he's really good with that anyway. And what he did with neural networks, in this case, this is a neural network. He wanted the neural network to speed up the topology optimization, right? So just as we saw that we can interpolate between different solutions, right? With that model, right? We have a model, we have an ellipse, and then 10 different solutions. He wanted to do exactly that. He showed the neural network that there are different results for different settings of the load and support. And then he asked the neural network what's in between, right? So what would be the other case? So with enough simulations input to the neural network, you are probably able to predict the output of the topology optimization of the stuff which was not seen exactly the same by the neural network, right? Now, as far as I remember, but don't quote me on that, I think that this is actually a bit of a stretch here, but I'm not sure. Like, I would have to ask Robert. But anyway, this is, let's say, when you teach a neural network, let's say with 10 different cases, and you ask the network after some time about those 10 different cases, it tends to be really precise with those cases. What happens in between those 10 cases can be really fuzzy and not really well informed. The more cases you have, the better, and you just close those gaps. But of course, you don't want to create all the possibilities, right? With, as we said, with 10 sliders or 20 sliders, 21 sliders like I had 100 to the power of 21 solutions. So I don't want to input all of them. I want to input 100 and get all of the other solutions for free. And that's what here is happening as well, but I'm not sure if this predicted one is exactly the one which was in the input set, in data set, or not. I have no idea. But anyway, it's a good approach. I think this is something which currently what I want to do with evaluation and design is, as we exactly have the second statement, assessment of its social ethical value. This is what I try to approach right now with asking the students, what do they think about the architecture which they like, right? I'm just collecting data right now. We'll see where it goes. Maybe it will be a failure. I expect it to be a failure, but anyway, we'll try what happens, right? What can I do with that information? I have some ideas, like, for instance, when I have a person writing down what would they like to see in their architecture, I could have a list of suggestions of different designs, how they solve those things which the person wants in different designs. We'll see how it works. In theory, it works beautifully, but in practice, it can be crap. Another way of using evaluation in design, or just speeding up the evaluation in design, is to, I mean, it's similar to what Robert wanted to do. Robert wanted to speed up topology optimizations. Samuel Wilkinson and Sean Hanna, that was Samuel's PhD, as far as I remember. He was trying to speed up CFD simulations. So we know that they can run for hours, and it's not really important to have a super, I mean, Formula One cars, that's where you want them to have super precise simulation. But with buildings, it's more important to get the general understanding, or where the turbulences could happen, or, you know, when you have wind tunnels where the wind pressure is increasing, and you want to just see more or less the general picture of what you are creating with putting any building in the city, right? So they made this tool where it could very quickly generate those CFD patterns, which were close enough to be useful, right? And by that, what they are doing by that is, in the traditional design process, first you come up with the design, you create the shape, then you use the, you know, you ask the structural engineer if it's correct, right? If it will not collapse. And then the structural engineer says, okay, it's a tower, so I have to make a CFD simulation as well. This is the next step. It takes a few days. And then the designer is informed that your tower should be 2 meters thinner, because it will collapse under the current, you know, with the currents, the center core, with that dimension, it will collapse, right? So, but if you have that kind of tool, which instantaneously, because it takes no time to generate it with your neural network, right? This pattern gives you a more or less depiction of how the CFD will look, then you move this entire chain closer to the architect, right? And here we can also link back, not really talking about that, but you know how there is an ambition of some people that the architect will become, one second, just center it a bit more, that the architect will become an engineer again, right? Just like in the medieval times, right? Where we had the, you know, the Gothic cathedrals, where there was a master builder who did everything from sourcing the material to building it and designing it, right? That some people think that the digital revolution which we have right now will bring architects back to that position. With the aid of computers, will be able to do everything. This could be a step in that direction. That's very speculative, let's say. Papers, you can take a print screen of that if you want to look at those papers. And yeah, so this is, I think this is it. Yeah, let's see the reinforcement learning one more. Yeah, just as a small detour from our topic, right? So we can see the, one second. If you know the channel 2 Minute Papers, it's a very nice channel. I just want to look for maze reinforcement. Yeah, this one. I mean, this is just, it's scary. If you look at it, it's scary. This is what it is. So, I mean, I'll just disable the voice. You will probably not see it in like full quality, but you can look for the title and, you know, just play it yourself. But I'll just play it here, and no voice. Yeah. So here, the scientists, computer scientists, they created a game where there are different agents and they try to do different things. So I think they play hide and seek. So once they see each other, I think the red ones try to look for the blue ones, and the blue ones try to, you know, hide, basically, right? The thing is that this is what they can do. So they can grab and move objects, and they can lock the objects. Right? I think there is some more rules to that. And they learn that, there is some score somewhere. They learn that they have to put the blocks, like there is, like, they only have the knowledge that they have to hide from the reds, right? They don't have a knowledge how to do that. So reinforcement learning is just trying different solutions, like what would give the blues the best hiding spot, right? So they learn by exploring, like if I move that here, will it improve my hiding position? If I move that here, millions of iterations, like or at least thousands of iterations. And you can see that after some time, they have some, there is some period where the reds are frozen, like here. So the blues can arrange the space as they like. But as the arrow points now, at some point, the reds will actually learn that they have a ramp. And you will see what happens, right? So at some point, the algorithm, there are two battling together groups, right? Two AIs, right? On two teams. One AI is hiding, the other AI is using whatever there is to find the other group. At some point, they have to. Okay, so why it happened? When the blues didn't know that they can lock themselves in this room, the reds didn't have anything to push them to use the ramp because they didn't have to use the ramp. So first, the blues started to put the blocks in the position and lock them, right? They learned that. And at that point, the reds were not successful enough. So they tried to explore the environment more and they saw that there is a ramp. Okay. And what here happens is that at this point, the blues learned that the reds are using the ramp. So before they lock themselves in, they take the ramp into the room so the reds cannot get it, right? It's all reinforcement learning. Like nothing of that is actually coded in there. The only thing coded is the aim, right? Hide or seek. And the rules like physics, right? So you cannot jump or something like that. That will also be, let's say, used by one or the other group. So more complex situations as well. Yeah, you can see that the blue is, yeah. So this, what happened right now, again, we can have a small replay. This is what happened right now. The game was never like the game was written so that the red or the blue person is always pushing or pulling the elements. But the physics of the game allowed some other actions which were not predicted by the person who wrote the game. And this is one of them. So you can see there is a ramp and there is the red agent. And the red agent jumps on top of the box. It actually exploits the bug in the game where when it's on the box, it can ride on it. So that's what it does. It's a bug in the game. Reinforcement learning just found this bug in the game and exploited it, right? So this is what we mean by good reinforcement learning with artificial general intelligence, right? We will have a problem with that. That's why, Elon Musk is going crazy about how AI is going to destroy the world. He's kind of right? If we don't do it properly, yeah, in theory he's right, but then in practice that's a different story, right? You can always pull the plug out, right? Kind of. That's the general consensus. But on the other hand, if you have a really smart artificial general intelligence, like again a speculation, if you have a really smart general intelligence, then we have imagine that there is a person walking in a room where there is a computer which runs the artificial general intelligence, which is way smarter than humans are, right? In theory, if the AI is smarter, what is the problem to convince the person that it's better not to turn it off, right? Of course, if the AI wants to kill the entire humanity, it's probably not going to success to convince that person that it's good. But maybe there are some other situations which are not as clear, right? And this is what we are actually scared about. We don't know those situations, right? So there is, yeah, blues log everything basically, and then they log themselves in. More and more complex strategies. They learn that the reds know how to write on the blocks, so they just do that. Anyway. So they just do that. Yeah, so what you saw here, the blues, they also learn how to throw the ramp out of the maze. So this is what is happening here. Here, also exploitation of the physics of the game. Not really predicted by the person who wrote the game. Yeah, I mean, you have to really watch this video again with the full commentary, and I think this is, yeah. You saw that, right? This just jump, exploiting the physics of the game again. It just jumps like above all the walls. Yep. Here, 1.1b, that means that there is 1.1 billion runs of this game. That just to show you the scale of the, the simulation, how long it takes to run it. Of course, it's running faster than real time. The animation here is just for our purpose, just to see how it works, but the computer runs it much faster, right? So anyway, more and more complex solutions, but you saw that reinforcement learning simply will exploit whatever there is. So if you are not careful with crafting the environment in which reinforcement learning works, it can do stuff which is not what you want it to do. Do we have a problem with that in architecture? Not really. But maybe with robots, maybe we will have, automated fabrication, and you will want to teach the robot how to build stuff, and then it will just throw the bricks, above your head or whatever, just to make it faster, if you don't code it properly. So this is actually something which I think that in architectural fabrication could have an application, even right now as an experiment, and it could go wrong. Like it could go wrong in a way that the thing will learn something which is incorrect, and it may cause some harm because, for instance, the virtual environment is not 100% exact as the real environment, right? So we also have to know what kind of things from the physical world we have to encode in our virtual environment. Anyway, I was talking for a bit long. So any questions right now?
Yeah, thank you for presentation. It was amazing. And yeah, my question could go for this reinforcement learning. If you little bit explain it more deeply, that I code that the algorithm start to make an action, and then I, in each iteration, kind of control it and update it.
Yeah.
Is it like that?
I can, yeah, we have this slide. This slide, actually, we skipped that slide, but we can just go about that. So we can have an example of, okay, let's keep with the example of this maze with those agents. So the environment in this case is the maze, but also environment is what you have to code to simulate the physics, right? So when the agents were really jumping on top of each other, that is the caused by the environment. So everything about what is happening, like what is the physics, what are the boundaries, is coded as the environment. Now, the agent was the reds and blues, right? The agent could perform some actions. So they could move, lock, unlock objects, and so on. And then by that action, they affect the environment. And then there's an interpreter. I mean, we usually don't write that interpreter, but there is some way of getting reward and the state, right? So in the most classical definition of reinforcement learning, the state is a discrete state. So let's say if you have an agent, the state will be where the agent is in the maze, right? In which square on the maze it is, right? And then if we have two agents, then the state, the full description of the environment with the state will be the two positions, right? So if you have 100 positions in the maze available and two agents, you automatically have 2 to the power of 100, no, wait, 100 to the power of 2, right? 10,000 combinations of those two agents in the maze. So that is the state. It shows you, it tells you there usually it's a usually classically is a discrete representation of the environment. The agent performs some action based on that state. Sometimes, but not always, it gets a reward. So it's up to you, the person who codes the algorithm, to define when the agent is going to get a reward, right? In the maze example, the reward for I think the reds were the seekers, right? So whenever the red is seeing the blue person, it gets a reward, right? And then the action can be, in this case, can be move left, move right, block, unblock. And that's it. That's all about that. It's only those things which are very easy to describe in abstract way. With some easy applications, they are very easy to code as well. It's like free functions, basically, right? But it's only that, nothing more. It's actually surprisingly simple, but it can do surprisingly well in some cases. Again, I don't really have, like with reinforcement learning, I don't really have a good application of that in architecture right now, in architectural design. I was thinking at some point, like when I did some workshops in the past, I was thinking that maybe we can use reinforcement learning to do some design. Like if we encode design as a step, like a discrete step, procedural design, right? When you have different procedures and they are discrete, maybe reinforcement learning can learn how to perform those different steps and which order. But I never really got to do that, and I never really like. The hard part is to describe what are those discrete steps. If you are using shape grammars, what's the like? Shape grammars could be a good environment, right? And the state is then, that's the question, what is the state? The action is which grammar to apply next, but the state, that's a challenge here, right? What is the reward, right? The simplest case, putting boxes on top of each other, right? You have a state which, let's say you have a voxel space of 10 by 10 by 10 voxels that gives you 1,000 possible locations for the boxes. But in the end, if the box is there or not, that's a binary switch. So you have 2 to the power of 100, yeah, 2 to the power of 1,000 possible combinations. That's way too much for reinforcement learning. Reinforcement learning, the classical one, works well with maybe 100 states. So you don't have really, like when you have more states, the learning time is just exponentially growing. Also, learning actions are performed usually initially in the exploration phase, so where the agents try to do different things, they don't have any understanding of the environment. Exploration is mostly random, right? So when you have a huge space, random exploration, like a random walking around this space, can take a lot of time. That's why they took 1 billion in this case. They took over 1 billion times to run the simulation because the state space was so big. There are ways to limit the state space, but it's really, really hard. Limit by, I mean, averaging it more or less with some smart algorithms. So this is it. Yeah.
Okay. So students, do you have any question?
I think they are sleeping now.
So then we can take like 10 minutes break, and
yes,
then we will continue.
Like even 15. My voice is just giving up.
Okay. Okay.
But let's take like quarter to one. At quarter to one, we'll go back and we'll start with some code. Actually, we'll run a Grasshopper.
Cool.
Yeah.
Thank you so much. It's really
Should we
interesting.
stop sharing or?
Yeah, we can. I will also stop recording.
How do I?
Okay. I mean, we can have a lot of conversation about this. Like I can imagine that you know, the AI will be implemented into the BIM, and you will draw just good plans because AI will always, you know, fix you and whatever.
Right now it's a huge speculation, I would say. I'm not saying
Yes.
it's impossible, but right now you saw that from those 10 problems we approached, 3 of them in a very good, like deep way, 7 of them are still unsolved. To run anything on a complex data set like a BIM model, it's, I think, beyond our capabilities right now. To do
Right
anything.
now. Mhm.
Yeah. Anyway, should we stop can I wait? I will mute myself and just stop the video, but I will leave the chat on.
Yes.
I will leave the app on. Okay, so let's meet in like 15 minutes.
Yeah.